let V be a Hermitian space. Okay, and well, given a Hermitian space, we already know something about this. What is that? Given a Hermitian space, exactly, yeah. So there exists an orthonormal basis, because a Hermitian space means the form is not only Hermitian on that, but it is an inner product. That is, it's a positive determinant form. Okay, and then we are defining. Well, at first, let T be a linear operator on V. Okay, and then T star the adjoint operator of T. So, since for example you were not in the last class, let's recall this, how we defined this T star. Okay. So, with respect to B, T has a matrix representation, right? Let A be the matrix representing T with respect to the basis B. Okay. Could you recall what is the relation between A and T? How we represented a linear operator in terms of a basis? So, B is your given basis and T is your linear operator. So, what is the relation with? I mean, how do you write? What is the equation that defines A in terms of T and B? Yes, yes. So, A is the linear combinations of the basis elements which represents this, the coefficients. Okay. So, how do you write that? TB equal to BA. Okay. The columns are giving you the coefficients which expresses the images of the basis in terms of basis itself. Okay. Do you recall this? This was done much earlier than the midsem. So, at first we considered linear transformations. So, TB was given by DA. D was the basis of the image space, not image space, the space where it, so the codomain. Okay, and now since we were in the same space, we are working with the same basis in both places. Okay, since it's a linear operator, so TB is equal to B, and this is called the matrix of T with respect to B. Okay, so now you know what is this matrix, right? What is A star? The adjoint of A. Okay. Okay. So we would define this T star in terms of that one. Okay. T star, the adjoint operator of T, is the operator from V to V whose matrix representation with respect to B is A star, okay, where A is the matrix representation of T with respect to B. Okay. So the next exercise, it's an easy exercise, so we will not do it in the class, but leave it for you. But it should be done. Okay. So what is the exercise we are going to give now? Wonderful. Yes. So exercise 1, show that T star is independent of the choice of the orthogonal basis, orthonormal basis, excuse me, orthonormal basis B of V. Okay. Thank you, Vishesh. So indeed, that is exercise, and it's not hard. You can do this. Okay. Another exercise also. It's also an easy one. So T star defined in this manner also satisfies this one. So let T and S be linear operators on V, then check these things. One, T star star, that is the adjoint of the adjoint, is equal to T. The second, T plus S whole star is equal to T star plus A star. And 3, Ts whole star is equal to A star T star. Okay. So these are rather simple and easy exercises. Please do both. Okay, not now. You can do them later. But they're rather simple and easy. Okay. Now let's recall some definitions of, some notions which we had both for matrices, and we are going to define them for linear operators as well. Okay. So here are matrices, and linear operators, and these are the notions. Okay. So maybe at first Hermitian. Hermitian matrix, A square matrix is Hermitian if A star is equal to A. Similarly, we call a linear operator Hermitian if T star, the adjoint operator, is going to be equal to T. Okay. We are just extending the notion from matrices to linear operators. Okay. Then unitary. What is the definition of a unitary matrix? A star A is equal to identity, right? So A star A is equal to identity. And similarly, we'll define a unitary linear operator as T star T equal to the identity operator here. Okay. And then something called a normal operator, which actually is a generalization of both of this. Okay. That is, for a matrix, A star A is equal to A star. Okay. It just, the matrices which commutes with its adjoint would be called a normal matrix. Okay. And similarly, the operators which is of this form T star T, which satisfies this equation, would be called normal operators. Okay. Now note that a Hermitian operator and the notion of a Hermitian operator or the notion of a unitary operator are just specializations of these ones. Okay. Because if T star is equal to T, of course then they commute. If T star T is equal to identity, then you will also get that T star is equal to identity as well. Okay. So these ones are just special cases of this one. here's, so we'll do a series of propositions, 3 propositions actually, which would lead us to the proof of the spectral theorem. The first proposition here. Okay. We are going to prove 3 different things for these ones. Okay. I mean, which identifies these operators. So at first, let T from V to V be a linear operator. Okay, any linear operator where V is a Hermitian space. Okay, and a Hermitian space with respect to the form. Okay. Okay. So then we have that for all VW in V, TVW is equal to V T star W. Okay. And VTW is equal to T star V W. Okay. Here we do not have any conditions on T. Okay. It's just a linear operator. Okay. The second one is that T is a normal operator if and only if TV is equal to T star V T star V. Okay. The third one, T is a Hermitian operator if and only if TV W is equal to V TW. Okay. And fourth, T is an unitary operator if and only if TVTW is equal to VW. Okay. So we already tried to prove the first one, it's easy. How should we proceed? Let B be a basis of V. Okay. Let's actually choose B to be an orthonormal basis, though we don't need it here, but for the next ones, yes. Yes. Which one? This T? T is not a constant, it's an operator, right? So it doesn't come out. Okay. Yes, we are going to use this matrix with respect to some basis. So we choose B to be a basis. For the first one, we can take any basis. For the next ones, we would take an orthonormal basis because we defined the adjoint. Well, actually, we defined the adjoint with respect to an orthonormal basis only. Okay, so actually, also for the first one, we require to choose an orthonormal basis. Okay, so let B be an orthonormal basis of V, and excuse me, let A be the matrix of the linear operator T with respect to B. Okay. Then we are going to write this in terms of, this one at first in terms of the matrix A. Okay. So let V be equal to Bx and W be equal to By. Okay. Then TVW is equal to what? What is this then? Recall that this is a Hermitian form and B was an orthonormal basis. Okay. So what is the gram matrix? Identity. Okay. So you don't have to bother about the identity matrix in between. You just work with the coordinates. Yes, wonderful. Ax star y, and that is x star ay, and that is equal to v tw, right? Sukrita, any problem anywhere? So this one, did you get it? What we are doing? We are taking the coordinates of this, taking bar transpose, multiplying with the gram matrix, which is identity. So there is, this is just identity in between. Okay, and then y, the coordinates of this. Right, yeah, thank you. Yes. Oh, okay, and here this star then, right? Yeah, thank you. Okay. So x star, a star, y, but a star was the matrix representation of T star with respect to the same basis. Okay. So V T star W. Okay. Similarly, what did we had? What was the other thing? Again, V T W is equal to Vishesh again. So how it should be? X star ay, that's equal to a star ax whole star, right? And that is equal to TV, T star VW. Wait a minute. What did we do? X star ay, it is a star x, excuse me, yeah, right. So this is a star x star y, and that is T star V W. Yes, now it's correct. Right. So that was the claim actually in the first one. Okay. So the first one is done. Now the next one. Okay, what was the next one? So proof of the second part. Okay. Well, here we can just use this one. Okay. So we are going to show that TV is equal to T star V and T star wait a minute. What did I write? Excuse me. TV TW is equal to T star V T star W for all V and W. Okay, excuse me. So then, well, this is of nearly of this form. We would just write T star there, and we'll replace there V with T star V, okay, and use the normality of the operator in some place. Okay. So from the first relation, this one, we get that T star V is equal to what? You tell me. So yeah, T star V, T star W, excuse me. Thank you, Vishesh. Yeah, T star V, T star W is equal to which one? No, just we are replacing V with T star V. So that will be T star V. This V is replaced by T star V. This one, we are just using this one. Okay. So there we have written T star V, and that comes just here. So T star V, comma W, right? Okay. T star V W, right? Now consider this one. Okay. Now we are looking at this one. Okay. Here it was VTW. We will consider now here TVTW. Okay. Again, TVTW. This is going to give us what? TVTW would here TVTW would give us T star TV comma W, right? Here we are replacing V with TW, TV. Okay. So here it will be just T star TV comma W, right? T star TV comma W. So we used both these things. This one in the first thing and this one in the second thing. The first thing replacing V with T star V, and the second one replacing V with TV. Just this we have written there. Okay. Until now we have not used normality. We just used that T is some linear operator. Okay. Now note that we know T star is equal to T star T. So we can equate these two things. Okay. Now when we equate these two things, we are just getting that this and this are equal. Okay. So this by normality of T. Okay. Thus T is normal. That implies that TV TW is equal to T star V T star W, right? But this was an if and only if condition. So we also have to go from there back. Okay. And we have seen that this one is equal to, we just saw above that this is equal to T star T V comma W, and this one is equal to T star V comma W. Okay. So normality implies that, no, not normality implies this. So we are trying to go back, and we know that these two are, if we are given that these two are equal, that means these two are equal, right? So from here we are trying to conclude the normality. Okay. But note that this is if and only if T star T V minus T star V comma W, that's equal to 0 for all W in W. In V, excuse me. What is W? For all W in V. Okay. What does this mean? This vector is perpendicular to every vector in V. So this one is in V perp, right? This one is inside V perp. Okay. Now what is V perp? It's 0, right? And why V perp is 0? It's an inner product space, right? Since this one is an inner product, in particular positive definite, that implies that V perp is equal to 0. That implies T star T V is equal to T star V for all V in V. For all the vectors in V, we are having T star T V is equal to T star V. That means this operator and this operator are equal on V. Okay. That is T star T is equal to T star. Okay. So, in other words, that reverses this implication. That is, if this two is satisfied, this is satisfied, that means T star T is equal to T star for, over V, and that means T is normal. Okay. That was the definition of a normal operator. Okay. So, thus the second part is also done. Okay. So, this implies the reverse inequality. Okay. This inequality. Reverse implication, excuse me. So, now the next one. Okay. So, the first and second is, are they clear to each of you? Okay. Now, third. Okay. TVW is equal to, well, express them again in terms of B, the basis B that we have considered. V was Bx, W was, which one? Yeah, sure. You can use 1, you can use 2, whichever you wish. Indeed. So, you can just use that TV is equal to V T star W, but T star is equal to T. Perfect, Vishesh. So, TVW is, okay, since it's a Hermitian operator, T is equal to T star. Let's write it down here, T equal to T star, and therefore, we have from here that we had earlier, TVW is V T star W by part 1, okay, and that is equal to V TW. Perfect. Thank you. And now the fourth one. Okay. So TV TW. Okay. Well, now which one you are going to use? Well, if you use this one, then you are just getting T star, right? But you can use the step in between. Here we did something, right? TV TW is equal to T star TV comma W. Okay. And that was proved for every linear operator, right? We have seen earlier that this is equal to T star T V W. But if this is unitary, that means this is equal to identity operator, right? As T is unitary. And so you have V W here. Now let's see whether the proofs go back, because we assumed Hermitian, we went in this manner, but whether if these two are satisfied, then whether we are getting this one as well. Okay, suppose these two are satisfied, then we are just having that V TW is equal to T star V T star W, right? We can apply the same trick as we done earlier. That is, the product of V with T star W minus TW is 0 for all V. So, should we write it down? Okay, it's understandable, right? So, you just have, I mean, from the equality of this and this, you are just getting that T star W minus TW is perpendicular to the entire vector space V. So this minus this should belong to the perpendicular V perp, right? Perpendicular orthogonal subspace. Okay. Orthogonal complement of V, but the orthogonal complement of V is 0 because this is an inner product on V. It's in particular positive definite, right? That would imply that this and this are equal for all W. Okay. Now W was arbitrary. That means T equal to T star on V. Okay. We are done. That is, it is indeed Hermitian. If this equality is satisfied, T is indeed Hermitian. Okay. From the equality of this and this. Okay. On the other hand, if T is unitary, suppose we are given this equality that EV_TW is equal to VW. Okay. And we would like to show that T is unitary, but you know that this is equal to T star V comma W. Okay. This one. This was also true for any linear operators. Okay. So you are getting this is equal to this. Okay. Given the equality, you are getting this part is equal to this part, and then we do the same trick again. We write T star V W is equal to VW. Take V to this side. It's linear in the first variable. Well, it's conjugate linear in the first variable. It doesn't matter because you are having the coefficients 1 in these cases. Okay. So this is some vector. This is some vector. Both are taken product with W. If they are equal, you can write that this vector minus this vector taken product with W is equal to 0 for all W. Okay. So that would mean T star TV minus V is belonging to V perp, but V perp is 0. Okay. Because it's a inner product space. Okay. And so T star TV is equal to V for all the vectors V in V, all the small vectors V in V. Okay, the given vector space, and that would mean that T star T is equal to the identity operator on the entire space. That is, this is a unitary operator because that was a definition of unitary operators, right? That is, T star T is equal to the identity operator. Okay. So both way we are done. Now the next part, I see that we cannot complete the proof of spectral theorem in today's class. We have to postpone it to the next one, but we can do one more proposition. Okay. So though we are doing spectral theorem, which are used to compress photos or videos, we couldn't compress our class to fit the proof in this one. Okay. The next question is rather simple. Do you recall what are invariant subspaces? Given a linear operator, what was an invariant subspace? Yeah. So just recall what is an invariant subspace of a right. So suppose T is a linear operator from V to V and W in V some subspace. Okay. So invariant W will be called an invariant subspace of T if TW is inside W. Okay. Now the thing what we are going to show is that if we have a linear operator such that W is an invariant subspace of T, then W perp is going to be an invariant subspace of T star and vice versa. Okay. So let's write it down here. Can I wipe this out or are you still completing? Okay, this was the first proposition. All right. So let T from V to V be a linear operator, and of course here V again Hermitian space with respect to a given inner product. Okay. Then, okay, also assume that W is a subspace of V. So let W be a subspace of V such that TW, okay, we don't need a such that because it's an if and only if statement. Okay. W is a subspace of V. Then TW is a subspace of W if and only if T star W perp is a subspace of W perp. Okay. That is, W is invariant under T if and only if W perp is invariant under T star. Okay. Okay, how do we show that? Well, we take an element of W perp and we are going to show that if you apply T star on that, that's still going to be in W perp. Okay. So let U be an element in W perp. Okay. Then to show T star U is in W perp. Okay. Now this one is in W perp, that means it's orthogonal to every element of W, right? So for all W in W, we have U W is equal to 0, right? Now that implies T star U W, what we will do with this? What we are going to do? Yes, it's a linear operator, it's an arbitrary linear operator, but we can of course do this, right? This means U comma TW, right? Okay. U, well, star of star, that will just give you T back, right? That was the first exercise, no, the second exercise, sorry. T double star is equal to T. So this one, but you know something, TW is in W, right? So this was in W because as TW is a subspace of W, right? And that means this product is equal to 0, okay. Because U was in W perp. Okay. So this is equal to 0. That means T star U is in W perp. Okay. And the other side of the proof is also rather simple. From if you have that this is inside this, exactly in a similar manner you can go back and show that TW is a subspace of W. The converse is also similar. Okay. So yeah, I think that's where we should end this class. See you in the next one where we finish the proof of the spectral theorem.